Chapter 4, Part 1, Data Acquisition Concepts. The production of a CT image of just one slice of anatomy actually requires a large set of data samples taken at different locations to satisfy the image reconstruction process. The total number of data samples per scan is given by the following formula right here. So the number of detectors times the number of data samples per detector equals the data sample. You can also find the data sample with this formula, which is the number of data samples per view multiplied by the number of views. There are three primary types of acquisition geometries, which are parallel beam geometry, fan beam geometry, and spiral or helical geometry. As a result of these types of acquisition geometries, a categorization of CT equipment has evolved based on the scanning geometry, scanning motion, and the number of detectors. We are going to discuss the 7 generations of CT scanners in these next few slides. Regarding the first generation of scanner, this is based on the parallel beam geometry and the translate-rotate scanning motion. Parallel beam geometry is defined by a set of parallel rays that generates a projection profile. Regarding the translate-rotate motion, this is where a single highly collimated X-ray beam and just 1 or 2 detectors first translate across the patient to collect the transmission readings. And then after one transmission is completed, the tube and detectors rotate by 1 degree and translate again to collect readings from a different direction. This is repeated for 180 degrees around the patient, and the whole process is then known as rectilinear pencil beam scanning. This was first used by Hounsfield in 1973, and it was used for a brain scanner. And the first exam took about 4.5 to 5.5 minutes to produce a complete scan of the patient. Second generation scanners are based on fan beam geometry and the translate-rotate scanning motion. On the second generation scanners had linear detector arrays, which were comprised of about 30 detectors, and they were coupled to the X-ray tube and to multiple pencil beams. The result of this is a beam geometry with a small fan whose apex originates at the X-ray tube, and the rays are divergent instead of parallel. And this formation significantly changes the image reconstruction algorithm from the first generation to the second generation. The fan beam translates across the patient to collect a set of transmission readings. And after the first translation, the tube and detector array rotate by larger increments than they did with the first generation, and then they translate again. The process is repeated for 180 degrees, and then this whole process is known as rectilinear multiple pencil beam scanning, since the tube traces a semicircular path during the scanning process. This results in shorter scan times, about 20 seconds to 3.5 minutes, and the time decrease is inversely proportional to the number of detectors. So the more detectors, then the shorter the total scan time is. Third generation scanners were based on fan beam geometry and the complete rotation of the tube and detectors. Fan beam geometry rotates continuously around the patient for 360 degrees. And here the X-ray tube is actually coupled to a curved detector array that goes around an arc of 30 to 40 degrees or greater from the apex of the fan. As the tube and detectors rotate, the projection profiles are collected and a view is obtained for every fixed point of the tube and the detector. And this motion is known as continuously rotating fan beam scanning, and the path traced by the tube is a circle instead of a semicircle like in the first and second generation scanners. The third generation scanners collect data faster than the first or second generation scanners did, and this increases the patient throughput and limits the production of artifacts caused by respiratory motion. There are 2 types of fourth generation scanners. Regarding the type of beam geometry for each of them. First, we will discuss the rotating fan beam, And here, the rotating fan beam is within a stationary circular ring of detectors where each detector gives rise to a fan. The beam is a wide fan where the apex of the fan originates at each detector. And as the tube moves from point to point within a circle, the single rays strike a detector. This results in short scan times, which varies with each scanner manufacturer, and the tube traces a circular path. The image reconstruction algorithm is for a fan beam geometry in this type of scanner, in which the apex of the fan is now at the detector, as opposed to the X-ray tube in the third generation. The second type has a nutating fan beam, where the apex of the fan is located outside a nutating ring of detectors. The detector ring tilts during the rotation, so the fan beam strikes the array of detectors located at the far side of the tube, while the detectors closest to the tube actually move out of the path of the beam. And here the term nutating refers to the tilting action of the detector ring during the data collection process. This type of scanner eliminates the poor geometry of other scanners where the tube rotates inside its detector ring near the object being imaged. The goal of multi-slice CT scanners is to improve volume coverage while improving the spatial and the temporal resolution than the previous generation scanners. Multi-slice CT scanners use spiral helical beam geometry, and they are continuous rotation scanners. And this is where data is collected in volumes rather than in individual slices. This type of scanner is based on slip ring technology, which includes the shortening of high-tension cables to the X-ray tube, which then allows for the continuous rotation of the gantry. The path traced by the X-ray tube during scanning is a spiral or a helix. And in spiral or helical beam geometry, the patient is transported through the gantry aperture for a single breath hold as the tube rotates. This results in a volume of the patient being scanned at once, and the beam actually becomes a cone in scanners capable of imaging 16 or greater slices per the 360-degree rotation, and this is known as cone beam geometry. Now we will discuss the different generations that fall under the multi-slice CT scanners. We'll start with the 5th generation scanner, and this is called a high-speed scanner since they can acquire scan data in milliseconds. An example of this is the electron beam CT scanner, where the data acquisition is a fan beam of X-rays produced by a beam of electrons that scans several stationary tungsten target rings. The fan beam actually passes through the patient, and transmission readings are collected for image reconstruction. Another example of a high-speed scanner is the dynamic spatial reconstructor scanner. And this was capable of producing 3D images of volumes of the patient, but however, it is now obsolete and not used. Just to go a little deeper regarding the electron beam CT scanner, the goal of it is to produce high-resolution images of moving organs free of artifacts caused by motion. This includes the heart, since it is always beating, and also with pediatrics, since it's hard for them to hold still. This type of scanner actually acquires CT data 10 times faster than the conventional CT scanners. The design is based on electron beam technology, and no X-ray tube is used, so there are no mechanical motions regarding the components, and the acquisition geometry is very different than those of regular systems. And take a look at figure 4.8 in your book. The computer for this type of scanner is capable of very fast reconstruction speeds, and the image reconstruction is based on the filtered back projection algorithm. More of these type of machines are actually expected to be distributed worldwide in the near future. So this picture is a basic configuration of an electron beam scanner. At one end of the scanner is an electron gun right here, and it generates about a 130 kV electron beam. The beam is accelerated, focused, and deflected at a certain angle by electromagnetic coils to strike one of the 4 adjacent tungsten target rings right here. These rings are stationary and span an arc of 210 degrees, and they can be used individually or in sequence with one another. So as a result, the heat dissipation is not an issue as it is in regular CT scanners. The detector array consists of 2 separate rings here, holding a 216-degree arc of detectors. The first ring holds 864 detectors, each half the size of those in the second ring, which holds 432 detectors. This detector arrangement allows for the acquisition of either 2 image slices when 1 target ring is being used, or 8 image slices when all 4 of the target rings are being used in a given order. Each solid state detector consists of a luminescent crystal and cadmium tungstate coupled optically with silicon photodiodes, which convert the light into current. And these are connected to a preamplifier. The output of the output from the detectors is then sent to the data acquisition system. The data acquisition system consists of ADCs, which are also known as digitizers, and they sample and digitize the output signals from the detectors. The digitized data is stored in random access memory, which can hold data for hundreds of scans in the multi-slice and also in the single slice modes. All of this information is then sent to the computer for processing. 6th generation scanners are also known as dual source CT scanners, and they solve the issue of artifacts when imaging cardiac anatomy. This is especially in regards to CT angiography, which are known as CTA studies on regular scanners. It has 2 X-ray tubes and 2 sets of detectors, and each is offset from the other by 90 degrees. So you can see here is a regular scanner where there is, here's the beam, here's the detectors. But in dual source scanning, you can tell that there are 2 separate X-ray tubes and 2 sets of detectors, and they are 90 degrees from each other. Moving on to 7th generation scanners. These type of scanners have flat panel detectors, and they're still in prototype and not currently being clinically used yet, but they may be used in the future. And these type of detectors, the tube and the detectors are coupled and positioned in the CT gantry. And the detector is made up of cesium iodide scintillator coupled to an amorphous silicon thin film transistor array. These provide for excellent spatial resolution due to the flat panel design, and they're also used in angiography to image blood vessels, where the image sharpness is especially important and crucial. Okay, slip ring technology, very important in CT. This type of technology allows for continuous gantry rotation in the spiral or helical CT scanners. We briefly discussed this a few slides back. This type of technology results in very fast data collection. It eliminates the long, high-tension cables to the X-ray tube that are normally used in the conventional start-stop scanners. The slip rings provide electrical power to operate the X-ray tube and also transfer signals from the detectors for input into the image reconstruction computer. The major advantage of this type of technology is that it facilitates continuous rotation of the tube so that the volume data can be acquired quickly from the patient. And as the tube rotates continuously, the patient is translated continuously through the gantry, which results in scanning in a spiral geometry. Other advantages of this type of technology include faster scan times and minimal interscan delays, the capacity for continuous acquisition protocols, the elimination of the start-stop process, which is characteristic of regular scanners, and the removal of the cable wraparound process. There are 2 types of slip ring designs. First, we will discuss the disc design, and this has conductive rings from the concentric circles in the plan of rotation. And then there is the cylindrical design. which includes conductive rings positioned along the axis of the rotation to form a cylinder. In both of these type of designs, the brushes transmit electrical power to CT components by gliding in contact grooves on the stationary slip ring. Take a look at figure 413 in your book to see an example of what I'm talking about. There are two common brush designs with slip ring technology. There's the wire brush design and then the composite brush design. Regarding the wire brush design, this uses conductive wire as a sliding contact, and then the composite brush design uses a block of some conductive type of material as the sliding contact. And a brush usually consists of one or more wires arranged so that they function as a spring with a free end against the conductive ring. Sometimes, though, the two brushes are used per ring to increase communication reliability or current carrying capacity. In the low voltage slip ring system, the AC and the X-ray signals are sent to slip rings by low voltage brushes. The slip ring then provides the power to the high voltage transformer or the generator, which then transmits the high voltage to the X-ray tube. In this type of system, the generator, the tube, and other controls are positioned on the orbital scan frame. In the high voltage slip ring system, the AC delivers power to the high voltage generator, and then the high voltage generator supplies the high voltage to the slip ring. And then the high voltage from the slip ring is transferred to the X-ray tube. And then in this type of system, the high voltage generator does not rotate with the X-ray tube at all.